to talk about carbide-free bainite today. This is a study that's been going on for quite a few years, and there are 3 labs involved, one from Canada, my lab, and also 2 from France. So the Institut Jean Lamour, which is University of Lorraine, and also there's the University of Rouen. So let me move on. I mean, I won't go through all the co-authors, there are too many of us. Yeah, it's not changing. Why won't it change? Here we go. So, quick introduction to carbide-free bainite steels. These are 3G steels, competitors to Q&P, also medium manganese steels. So, the first thing you want to do is to produce a fully austenitic microstructure. Now, in this talk, we're doing a lot of diffraction, X-ray diffraction. So, when we're using synchrotron X-ray diffraction, we want to have the smallest grain size possible. So we have to control the austenitization step, and we did it at 900 degrees C. So it's not optimal for, as we'll see later on, dissolving all of the vanadium precipitates, but it does control the austenite grain structure. So that's why we did that. Then we go fast cooling. So we can cool at 50 degrees C per second. So we use special hollow samples in a dilatometer that's installed in the X-ray beam line. So we could control at 50 degrees C per second. That means no ferrite is forming, no perlite. Okay, then we have our isothermal hold. Now these steels have always got silicon in, so the austenite will decompose to bainite, essentially carbide-free bainite because of the silicon. So we should hopefully have no cementite or very little cementite involved. These temperatures that we're using are, as you'll see later on, very low, between 375 and 430 degrees C. These are too low for vanadium precipitation. So all the vanadium I'm talking about in this presentation is going to be in solid solution, all of the effects. And then at the end of the transformation, there's a stasis. It doesn't go to completion. We'll have so we will have some austenite that is not transformed. And as we cool down to room temperature, some of that untransformed austenite may be unstable and transformed to martensite during the cooling. So we'll have essentially a 3-phase microstructure at the end. We have a bainitic ferrite, austenite, and some martensite. Okay, that's what. So one of the first things to think about is if we're looking at vanadium in bainitic steels, is what we already know. And there's a lot of work being done on very low carbon bainite steels. So these would be things like line pipe steels like X80. And what we know is that adding vanadium to those steels does improve the mechanical properties. They get stronger. And the reason for that is nothing to do with precipitation. It's simply because we have increased hardenability due to solid solution vanadium. And we also have this temper resistance effect of vanadium that's well known in martensite, but it also applies in bainite. So here's some data that has been published in 2018 from our group at Canmet. This is Fateh Fazeli, who's the lead author. And you can see the effect of the vanadium on the TTT diagram. And also here is very clear what's happening is when you look at the dilatometry data, the BS start temperature has been dropped from 580 to 552 degrees C. It means that you're getting more lower bainite, essentially, and that's where your strengthening comes from. And then there is this tempering effect as well. These are in situ compression, hot compression, done. So this is the bainite aging time, if you like. This was at 450 degrees C transformation for a 0.06 vanadium steel, 0.06 carbon as well. And you can see that we've got some gain from having vanadium in solid solution in terms of the softening kinetics of the bainite. Now, carbide-free bainite steels, obviously you need more carbon. And usually you're looking at least 0.2 weight percent, sometimes more. We know that vanadium won't precipitate in a normal CFB cycle. That's quite clear from the thermodynamics. But when we do the actual measurements, we do see that adding vanadium does make these steels a little stronger. So here's some hardness data from the composition I'm going to talk about today. This is the air-cooled hot rolled condition, and then this is the transformed condition, transformation at 375, 400, and 430 degrees C. And you can see the strength actually increases as the transformation temperature decreases, but the vanadium does give you a benefit at all of those temperatures. So this is the grades we'll talk about today. 0.2 carbon, 2 manganese, 1.8 silicon, without vanadium, and with vanadium, 0.15 in this case. Very low nitrogen. We don't want vanadium to precipitate, so we don't add nitrogen here. This is called the reference alloy. This is the reference plus vanadium alloy, ref plus V. So moving on. We did quite a lot of microstructural investigations on these steels, and I won't go into all the details of that. If you want, they've all been published. There's a metals publication in 2020 that you can look at. When you do SEM, when you do EBSD, essentially you don't see any difference from the addition of the 0.2 vanadium. It's all lower bainite. You don't see any difference in the lath size or the effective grain size of the bainite, nothing at all. So you can't really see any major difference of vanadium in the optical or in the SEM microstructure. If you go to the TEM, which is what you do next, and you can see this nice lower bainite structure again. We measured the lath thickness. So this was done in the TEM for all the temperatures and for the two alloys. We couldn't see any effect. There's no obvious influence of vanadium on the bainite lath width, either in the TEM or in the SEM. So that's quite clear. Doesn't change anything there. We did a lot of precipitation studies as well. So here's an example, bright field image. You can see retained austenite. These are these dark laths here. And then there's bainitic ferrite between them. You don't really see any precipitation or strong precipitation in this image. This image here is a chemical map. So we're doing an EDX map with vanadium. And so the red color is where you see locally higher concentrations of vanadium. And you can see some segregation of vanadium. It looks like precipitates. But when you look at the carbon map, the associated carbon map, then you see carbon enrichment in the austenite laths, the retained austenite laths, but you don't see these precipitates as being carbides. So we don't think they are. Some of them are probably from the hot strip that were undissolved, and maybe along this line here, if they're in a linear type of constitution, then that might be from hot strip precipitation. But the rest of them we don't think are precipitates. And we didn't detect any very small precipitates that would be important for strengthening. We did a lot of atom probe work. So actually 42 different atom probe tips were prepared and run successfully. So here's just an example of the data that we got from the atom probe. This is quite a nice TEM image because you can see all three phases in one image. So you have bainitic ferrite, then you have retained austenite, and you have regions where that retained austenite is transformed to martensite, so alpha prime. And these are typical atom probe images from each phase. So the austenite carbon is uniform. In the martensite, carbon is not uniform, but is very, very dense. And in the bainitic ferrite, you can see regions where you've got strong clusters of carbon, but there's also regions where there are uniform carbon, apparently. Oh, excuse me. Right, so I'll move on from that. Now, the high energy X-ray diffraction. So we've got these in situ experiments where we're heating up and then cooling down the specimen essentially in a dilatometer. And we can measure the variation in the austenite lattice parameter or the ferrite lattice, everything that you might want in the typical XRD experiment. Here is the thermal cycles. So the black is at 375, which is just above MS in this case. The blue is at 400 and the red is at 430. And this is the body-centered cubic fraction, the if you like, bainitic ferrite fraction. So you can see quite clearly that the amount of bainite will increase as the transformation temperature decreases. That's quite clear. There doesn't seem to be a very strong effect on the kinetics of that transformation. It's pretty much complete by 180 seconds in all cases. The dotted lines here are the reference steel, and the solid lines here are from the steel with vanadium. So all you can really say is that at the end of transformation, the amount of bainitic ferrite, or conversely, the amount of retained austenite, is essentially the same. It's unchanged by the presence of vanadium. But there is a difference. If you look at the higher temperatures, you can see at this point here, where you get into the cooling stage, this is martensite forming. It's not bainitic ferrite, this is martensite. So we end up with the same amount of retained austenite, but we have a little bit more martensite when we add vanadium at the higher temperature. I think that's probably everything. So this is the data from, you can see, you actually see the numbers there. And here, now we're looking at the carbon content in the austenite. So we get that directly from the austenite lattice parameter. And using this simple equation here, it's well known. And you can see quite a few different things in this graph. The first thing is that the austenite, that's the retained austenite, is still being enriched in carbon long after the transformation is finished. So as I said, the transformation finishes about 180 seconds, you get to stasis, but we're still enriching the carbon, the austenite in carbon, which is kind of interesting. Again, at the lower temperatures, here we've got a smaller austenite fraction, but we have a higher amount of enrichment in the austenite carbon content is higher, logically. And there is something quite interesting to do with vanadium. If we look at the dotted curves here, when you don't have vanadium, the retained austenite seems to achieve a higher end carbon composition, slightly. It's not huge, but there is a systematic increase in the carbon at the end of the transformation when vanadium is not present. When vanadium is present, we have less. So what we say from that is the vanadium addition seems to slow down the partitioning kinetics. Now, because we're not forming any ferrite during the cooling, we can calculate what the carbon content in bainitic ferrite has to be, assuming there's no precipitation, at stasis, just from a simple mass balance equation. And these are the numbers that you can see here. So what you can see is that quite a significant amount of carbon in the bainite, 0.1 or more. There doesn't seem to be any real difference between the two, reference or reference plus vanadium. And we have a decrease in the carbon content as the transformation temperature increases. We did a similar experiment ex situ using electron energy loss spectroscopy in the TEM. So I won't go through this because I don't have time to go through all the data. I don't have time to explain it all. But what you can see is the round points here. This is the retained austenite. The triangular points here are from martensite, and the diamonds here are from bainitic ferrite. So you can see the evolution of the carbon content and the difference between the three phases. So now this is the full data set that we've actually just recently published. So this paper has just come out within the last few weeks in 2023 in Scripta. It compares the high energy X-ray diffraction, the EELS, and the atom probe for the same samples. And what's kind of interesting about this study is it's the first time all these three techniques have been used in parallel. And it's also one of the few studies where you have a significant amount of statistics in the data. So the numbers in the parentheses, these are the number of samples or the number of areas that we've actually examined. So you can see, for example, the atom probe areas, we've got 12 different areas for one sample, for example, there. If we look at the trends, look at bainitic ferrite first. So we've got the carbon content against the transformation temperature. The solid curves here, the solid blocks here, if you like, are from the reference steel, and the open ones are from the vanadium steel. we can't see any clear influence of vanadium on the amount of carbon that we measure in the bainite. We don't see any real difference at all. These error bars here, this is not measurement error. This is the actual dispersion in the data. So this is showing you that these values are quite dispersed. In other words, the carbon content in bainite is not uniform. It varies from lath to lath, and it varies by quite a lot. If we look at the retained austenite, when we add the vanadium, then what you could say is there's a very slight decrease in the austenite carbon content. It's very slight. It's not major. The atom probe data here in green is a little bit higher than the other two techniques, but that's because we only had about 2 islands that we found in atom probe that were martensitic. So, austenitic. So that explains that. It's a statistics effect. So we compared our values that we found with what's available in the literature. There isn't very much for low carbon bainite. There's a lot of data on high carbon bainite because it's a lot easier to work with. But on lower carbon bainite like this, it's not so easy to find. So, but we did find 3, and we've compared our values here. So the solid, again, the points, the colored points here, this is our data from the 3 different techniques that we used, and the open points are from the literature. So it's consistent. We don't find a huge difference. One thing that we would like to look at further is the fact that all of the X-ray diffraction, the high energy X-ray diffraction data seems to give higher values for the bainitic carbon, the bainitic ferrite carbon, than the EELS or the atom probe techniques. So that's something that seems to be systematic and is quite interesting. All of the data that we've got so far predicts a high carbon content in bainite, even with these low nominal 0.2 carbon steels, much higher than para-equilibrium would predict. So this carbon is obviously lost for austenite stabilization, although it may contribute to bainitic ferrite strength, depending on whether it's clustered, precipitated, or in solid solution. We don't, in this study, we don't make any difference between the state of the carbon in the bainitic ferrite. We measure it all. So, okay, why does vanadium make these steels stronger? Well, we know it doesn't change the transformation kinetics. It doesn't change the final fraction of retained austenite. There's a slight difference in the Ra final carbon content, fractional difference in the amount of martensite that's formed at higher temperatures, but not really at lower temperatures. No change in the bainite lath widths, no change in the bainitic, or no measurable change in bainitic ferrite carbon content, and no significant precipitation of vanadium. So there's only really one thing left, and that's the dislocation density to check. So, excuse me, my time's nearly up. So we use Williamson Hall to do that. And so this is some of the raw data. And the result is shown in this graph here. So here are the 3 transformation temperatures, 375, 400, and 430, with the 2 grades. And you can see that the vanadium grade has systematically higher dislocation density. Compare that with the hardness data, they could almost be superimposed. Almost, not quite. So what we can say is that dislocation density measurement strongly correlated with the measured hardness behavior. That's obvious. We have an inverse correlation of hardness with the mean carbon content in retained austenite. That's very interesting. What we also can say is that the vanadium additions increased the dislocation density at all the transformations temperatures tested. This is a similar effect to what we see in low carbon, the very low carbon bainite steels, the X80 that I showed you at the beginning. But the mechanism is not the same. It's not because we're delaying the bainite start. It's quite obviously not that the case in this study. So we have a very complicated behavior. There's at least 3 competing mechanisms involved. So what we see is that vanadium slows down the carbon partition to retained austenite. So the retained austenite is softer. So during the transformation, it's easier to deform, and that should reduce the overall dislocation density. At the same time, that retained austenite is slightly less stable, so you get more martensite forming during the cooling part, that will increase the dislocation density, especially at higher temperatures. It won't have a big effect at low transformation temperatures. The vanadium in solid solution, plus possibly an increment of bainitic carbon, slows down the static and dynamic recovery in bainite, and that's going to increase the dislocation density. And the balance of all those three effects, and possibly other ones, is what determines the relative increase in strength when you have vanadium additions. So this is my last slide. We can actually go a bit further with this study because we have statistical data. So if we look at the sample, we have the best data. This is the reference sample, no vanadium, transformed at 375 degrees C. We have 12 atom probe tips, and we measured 12 different bainitic laths with the yields. And these are the average carbon contents that we found from the two techniques. They agree pretty well. But if we do a statistical analysis where we divide those data up into, I think it was 0.05 weight percent blocks and plot the cumulative graph, then we get these two distributions. So the blue triangles, that's the yields distribution, and the red is from the atom probe data. They do follow a sigmoidal type of distribution. But when you look at the 50%, the median value, you get something about 0.07 weight percent carbon in bainitic ferrite, which is smaller than both of these and significantly smaller than the APT. So that means that the bainitic carbon content doesn't follow a normal distribution. That's very interesting. And I think that's the very first time ever that's ever been shown. So excess carbon trapped in bainite does not follow a normal distribution. There's a bias towards lower carbon contents. What could that be correlated with? We don't know yet. It could be with lath width, because we know bainitic lath widths are not, don't follow a normal distribution either. That's work that needs to be done. But what is sure is that carbon varies widely from region to region, lath to lath. And that's a new finding. So conclusions, we've studied the influence of vanadium on isothermally transformed CFB. We used 3 different techniques at very different length scales. I didn't mention that, but you're looking at cubic millimeters in the HEXRD. In the TEM with the yields, you're looking at the micron and submicron type scale. And with the atom probe, obviously, you're at the nanometer range. So all those 3 techniques give the same basic result. There's a large fraction of bainitic ferrite with supersaturated carbon contents, even at high transformation temperatures and at these low carbon nominal steels. The carbon content doesn't seem to be strongly influenced by the vanadium addition, which is maybe surprising considering how strong carbide former vanadium is, but we don't see it. The effect of vanadium in carbide-free bainite, well, you get an overall strengthening effect, but it's not anything to do with the kinetic stasis, final phase fractions, bainitic lath size, or even bainitic carbon content. It's not that. It's not precipitation strengthening either. We do see a change in the rate of carbon partitioning to austenite and maybe a slight reduction in the final austenite carbon content. But the main thing is this dislocation density is changed. It's increased at all tested temperatures. And the reason for that increase is not completely clear yet. It's complicated. But we do see quite clearly that the final mechanical properties correlate very well with the density, and there is an inverse correlation with the retained austenite carbon content. So thank you very much for listening. I hope I got through in the right amount of time.
Yeah, and thanks for Dr. Colin Scott. Very nice talk about many techniques has been presented to check, examine the carbon and the carbide-free bainite in the steel. I think we are almost run off all the time. So if anyone has a question, please directly contact the Dr. Colin Scott for his talk. And we have to move to the next talk. Thanks for Dr. Colin Scott. Move to the next one.